All right, we're going to begin this chapter by working with limits, the limit of a function. And the idea of a limit is that, so if we have some function f of x, if that function, if like the output values of that function become arbitrarily close to some number L as x approaches some input c from either side within the domain of the function, then the limit of the function, the limit of f of x as x approaches c is L. We write it like this, right? So we have the limit, we just write lim, and then underneath that x with a little arrow going to c, so the limit as x approaches c of f of x, whatever our function is equal to L. Now, here's what we mean when we talk about that. If we look at it, if we have a graph of this function, we're saying that as we kind of let x zero in on this input value c from either direction, if you kind of trace along the graph here from either direction, the output values, the y coordinates, zero in on this value L. So this is sort of an intuitive kind of way to define the limit, and I think it's a helpful way to think about it. I'm also going to just write out another way to define it, a bit of a more rigorous definition. You'll probably see this definition maybe in our textbook. We call it the epsilon delta definition. The epsilon delta definition of a limit. And this just says that the limit as x approaches c of f of x is equal to L if for every epsilon greater than 0 there exists a delta greater than 0 such that absolute value of f of x minus L is less than epsilon whenever absolute value of x minus c is less than delta. So let me explain what this means, right? So the first thing that we need to understand is this absolute value of this difference. So just in general, absolute value of a minus b. If you're looking at the number line, this really gives you the distance between a and b on the number line. And so the idea behind this definition is that let's say somebody says, all right, if the limit is L, right, if the limit of f of x as x approaches c is L, tell me how I can get within, some distance of L. I want to get really close to L, right? This is for every epsilon greater than 0. The idea is that somebody could pick an epsilon really, really small, right, and kind of make this epsilon window around L, so that like this value here is L minus epsilon and this value here is L plus epsilon. And the idea is they say, okay, I want to get within this range, within this window of epsilon. You kind of build an epsilon window around L. And if the limit really is L, then I can find a delta, so that if you're within delta distance of c, you'll be within that epsilon window. And we can kind of just really in this graph kind of trace that down. So here is c minus delta, and there is c plus delta. So what's really important to understand about the limit of a function, right, is this idea of getting close to a value. And I can get as close to that limit as you want, as long as I can get close enough to c. And implicit in this definition, the idea behind it is that we don't even need the function to be defined as c. F of c doesn't even have to exist in order for the limit to exist. And we'll see why in the next example. So in example 2.1, we are asked to compare the values of the limit as x approaches 3 of f of x and the value f of 3. So when we look at this graph, we could see that our function is more or less just a nice smooth continuous curve. The interesting thing happens when x is equal to 3. So for all values except for 3, the function just lies on that smooth curve. At 3, there's this hole, so f of 3 is not actually at the value in that hole. F of 3 is defined to be up here at the value 2. So f of 3 is 2. That's what it means when they write the little solid dot up there. However, the limit as x approaches 3 of f of x is, let's see, if we let x zero in on 3 from either direction, right, and kind of trace along the curve, then the y coordinates are approaching 1. So here's an example of a function that is defined at 3, but the limit of the function when x approaches 3 is not the same as f of 3. In fact, if we made a slight change to this, I'm going to just sort of quickly sketch out a different function. I'm going to try to make it look pretty close to this. So here I'm sketching out a really similar function. I'm doing something similar in that there's a little hole right in the graph, so the function f of 3 is not 1. But this time I'm not even filling in the solid dot anywhere. So in this graph on the right side here, the limit as x approaches 3 of f of x is equal to 1. The limit is 1, right? That's what the y coordinates are approaching. But in this case, f of 3 does not exist, right? We can't plug in we can't plug 3 into the function. So the limit gives us this ability to talk about how close something what is getting, like what our values are approaching, without having to be concerned about the actual value of the function or even if the function is defined. This graph on the left that we started with, and in fact also the graph on the right, give us examples of how a function might be not continuous at a point. So a function is continuous. Sort of our intuitive sense of what it means for a function to be continuous is that it's a nice smooth curve. We could like sketch it out or trace over it without having to lift our pencil from the paper. Both of these graphs are continuous at lots of values, right? If I focus on this graph on the left, this graph is continuous all the way up here, right? And then leading out, like, nice smooth curve. That's continuous. The problem is right here. It's not continuous at x equals 3. I'd have to jump and to get that output at 2 and then kind of jump back down to get back onto the graph. Similar for this graph on the right. It's continuous up until you get to 3. Then I have to kind of jump over that hole and then pick up where I left off on the other side. So we could kind of detect continuity issues by looking at the graph. We say that a function is continuous at a point, C, if all 3 of these conditions are met. First of all, f of c has to exist. Like I have to be able to plug in c and get out a value. The limit as x approaches c of f of x has to exist. I have to be able to approach c from either side right, and get a value. I have to be able to evaluate that limit, and those two things have to be the same. The limit as x approaches c of f of x has to equal f of c. So that's what it means to be continuous at a single point c. A function is continuous on an interval if it's continuous for every value on that interval. So up here, the graph on the left, this is continuous everywhere except at 3. Similarly, the graph on the right is continuous everywhere except at 3. For the graph on the left, the limit exists and the function exists, but it fails that third criteria because those values are different. For the graph on the right, this is not continuous at 3 because f of 3 does not exist. On the next page, we're going to do some examples where we consider the continuity by examining graphs and then by examining the algebraic expression of a function. So in part A, so for all of these parts, right, we're going to determine the values for which each function is continuous. For a value where the function is not continuous, determine the reason. So the first one, this is a nice smooth curve. Now, the function doesn't exist for values less than 1, but I think that just means its domain is restricted. So this really is continuous everywhere on its domain. And the domain is x greater than or equal to 1. Right, there's no jumps, there's no holes there. It's a nice smooth curve. In part B, we could detect a little bit of funny business happening when x is equal to 1, right? Like I can't trace the whole function without having to lift my pencil off the paper here. So this is not continuous at x equals 1. And we'll note that f of 1 does exist. F of 1 looks like it might be around 4.5 or something. But the limit as x approaches 1 does not exist. It does not exist because as I approach 1 from either side, right, when I approach 1 from below, the outputs are getting closer and closer to 3, but as I approach 1 from above, the outputs are getting closer and closer to this value, maybe about 4.5. So in order for the limit to exist, you have to approach the same value from either side, and we're not, and that doesn't happen here. So it is not continuous at x equals 1. Part C. Maybe take a few seconds and see if you can determine where it may or may not be continuous. So this function is not continuous at x equals, I guess that would be -2 here. It's not continuous at x equals -2 because the function is not defined at -2. Or in other words, f of -2 does not exist. And we'll just note here in these two parts B and C, we determined where it was not continuous. In both of these, the function appears to be continuous everywhere else. Now, these last two, we are given not a graph, but the actual kind of algebraic expression of this function. So in part D, our function is 1 over x minus 2. Certainly, one way we could help ourselves to see if it's continuous is by looking at the graph. But we can also detect some weird things, potential problems, by just examining the expression. Note that in the definition, the first part is that f of c has to exist, right? We have to be able to plug in the value and get an output. So in part D, we could see pretty quickly we can't plug in x equals 2, so it's not continuous at x equals 2. And that's because f of 2 does not exist. This function is continuous everywhere else. If you throw it in the calculator and look at the graph, you'll see everywhere else it does look like a smooth curve. Also, we could kind of, analyzing this algebraically, there's no problems with plugging anything else in. In part E, this is the function f of x equals 3x squared. It's a nice quadratic. We're not dividing by x, right? There's no x's in the denominator. So there's nothing funny that can happen. They're not in any danger of dividing by 0. So this is actually continuous on all real numbers. Right, there's no jumps and there's no division by 0. In fact, all polynomials of any degree, they're always continuous on all real numbers. So we've talked about what a limit is, and we've talked about what the limit has to do with continuity, and discussed continuity of different functions. Now the rest of this section we're going to work on evaluating limits. Now there's a couple ways to do this. There's one way that we can kind of estimate a limit or develop a good hunch about what a limit is, and that is to do it numerically. After we see how to evaluate a limit numerically, we're going to move pretty quickly and then focus on evaluating a limit analytically. That is the way that we really want to evaluate a limit. But first we're going to kind of just get our feet wet, kind of trying to work with what a limit means. What does it mean to say, I'm getting close to the value 3, and then seeing what happens to the outputs? And this is really almost like a plug and chug kind of a thing. I'm going to make a little table. In the top row, I'm just going to have values of x. Now, we'll just note, we want to evaluate the limit as x approaches 3, and I need to be able to approach 3 from either side, from below and from above. So if I approach it from below, I'm going to plug in numbers like 2.9, 2.99, 2.999. And if I approach it from above, I'm going to plug in values like 3.1, 3.01, and 3.001. So you can see in the top row, I'm kind of letting x get closer and closer to 3. What I'm going to do now is use my calculator to just have to spit out the values. Now, I could just sort of plug in and the whole function, right? Like plug in, 2.9 squared minus 9 and divide it by 2.9 minus 3, and then do the same thing for all of these inputs. I'm going to try to do it a little bit quicker. I'm going to streamline this process, and I'm going to start by just plugging in that expression to my y equals editor. So I'm putting it in y1 here, and my numerator needs to be in its own set of parentheses, x squared minus 9. My denominator needs to be in a set of parentheses, x minus 3. So there's my function. Now I'm going to quit to my home screen. My calculator, I can tell it to evaluate a function at a some some value that I plug in. I can have it give me the output. And the way I do that is I hit the vars button, which is right next to clear. It's the one in red right now. I arrow over to yvars. I put in a function, so I hit enter. And then I put mine in y1, so I'm going to hit enter there. And then this is function notation, so parentheses, my input, 2.9. And then I close my parentheses and hit enter. My output is 5.9. I could do the same thing for all the others. Vars, yvars, function, y1, parentheses, 2.99. And then I get 5.99. And if I'm doing the same thing over and over again, the same kind of set of keystrokes like I am to bring up the function, I could just bring up my last entry. If I hit second, enter, it'll bring up the last thing I plugged in, and I could just kind of edit it as I need to. So 5.999. So from below, it looks like it's getting close to 6. Let's see what's happening from above. I'm going to put in 3.1. .1, 3.01. Whoops. Hit 6.01. And I think nobody will be surprised when we find out that when we plug in 3.001, we get 6.001. So now the the outputs appear to be approaching the value 6. So we could certainly say, like, it appears that. It looks like the limit as x approaches 3 of x squared minus 9 over x minus 3 is equal to 6. Now, we don't want to rely on evaluating limits numerically. And the reason we don't want to do that is because it's, functions can have really odd behaviors. And it could be that this function does something really wild as you get close to 3, but maybe you don't see it until you get really super extra close. It is impossible for us to plug in all the values approaching 3, right? The real numbers are kind of, there's this continuous, it's a continuum, right? So I can, as close as I might be getting when I actually plug in values, there's closer values. I can always get closer. So we don't want to rely just on evaluating limits numerically. We have another way to evaluate limits, and that's going to be our focus for the rest of this section, is on evaluating limits analytically. So first we're going to just recall that if a function is continuous, then the limit is just equal to the output at that value. So we can evaluate some limits just by plugging in the value. All polynomials are continuous, and any function that is continuous at the value that we're interested in, we can always just plug in that value. So in example 2.4, we want to evaluate the limit as x approaches -2 of x squared plus 2. X squared plus 2 is a polynomial. It is continuous everywhere, and so this limit, we're just going to plug it in. So this is -2 squared plus 2. -2 squared is 4, so we get 6. So the limit as x approaches -2 of x squared plus 2 is equal to 6. If our function is not continuous at the value we're interested in, then sometimes we can do some algebra and rewrite it in such a way that allows us to plug in that value. So in example 2.5, we're going to revisit the limit that we did numerically up here. All right, so this is the same limit. And, this limit, our function is x squared minus 9 divided by x minus 3. If we were interested in any other number except for 3, we could just plug it in because it's continuous at that value. But we're interested in what's happening at 3. That's sort of naturally, I think, the value we should be interested in, right? We could tell something wonky is happening at 3. What we're going to do is some algebra. So we're going to rewrite this. As I rewrite it, I'm carrying the lim through, right? I'm writing lim at every step. The algebra I'm going to do is some factoring. So the top is a difference of squares, so I could factor that as x minus 3, x plus 3. This is over x minus 3. And now I can see I've got a common factor of x minus 3, so let's cancel those. And this is equal to the limit. I have to write the lim at this step. And I'll talk about why we have to write that every time in a moment. But now we want to evaluate the limit as x approaches 3 of x plus 3. X plus 3 is continuous at 3. There is no problem letting x equal 3 at this step. So we're going to do it. And it's at this point, once I actually let x equal 3, I no longer write the limit. So this is 3 plus 3, or 6. So as it turns out, our hunch from up here is correct. The limit is, in fact, equal to 6. Now here's why we have to write the limit at every step and up until we let x approach 3. And that is to compare this with this. Right? Let's just talk about these. X squared minus 9 over x minus 3 isn't always equal to x plus 3. It is equal to x plus 3 everywhere except for when x is equal to 3. Right? This function right here is not defined at x equals 3. And we can't plug 3 in there. But this is defined at x equals 3. And in fact, it's continuous there. So they're not identically the same function, right? They're the same everywhere except for the actual value that we're interested in, right? Like, I'm interested explicitly in what's happening when x is getting close to 3, so I really have to carry that lim through. Otherwise, I'd be sort of making a statement that is not accurate. They're not the same function, but their limits as x approach 3 is the same. Let's try another one. When we evaluate limits analytically, really the name of the game is doing some algebra to make it look different. Now, our algebraic path through this problem, actually, we have some choices. We have a couple of options. One option is you could FOIL out, expand out the 4 plus x squared, simplify the top and then see if it factors. It will. Or you could factor it right off, because this is actually also a difference of squares in this numerator. Also, I'm just going to point out that this is the limit as x approaches 0, and for that reason, we actually do need to do algebra. The first thing you want to look at is, can I just let x approach this value right off? In this case, we can't, because that would make us divide by 0, and so this is why we have to do some algebra to help us out. Up top, if I factor it as a difference of squares, because 16 is 4 squared, this will look like 4 plus x minus 4 times 4 plus x plus 4 and doing some simplifying, 4 plus x minus 4 is x, and then 4 plus x plus 4 is x plus 8. We can cancel the factors of x. So this is the limit as x approaches 0 of x plus 8. And of course, if we let x approach 0 now, we get 0 plus 8, or just 8. So that's what this limit is equal to. The other option, as I mentioned in the beginning, was to actually expand out 4 plus x squared. So that's 16 plus 8x plus x squared, and then minus 16. Oh, I wrote divided by 8 at the bottom. Obviously that's x. And the 16 and the minus 16 will cancel each other out. And we have 8x plus x squared is x times x plus 8. And then, of course, now we're back at where we were in the other step. All right, so these are we did a couple of examples of a limit as x approaches some fixed number. And the idea is to do some algebra. If you can't plug in the actual value that you're interested in, because it would make you divide by 0, you want to do some algebra, see if you can't do some factoring and get that problem factor to cancel. The other type of limit would be limits as x approaches infinity. And what these limits are is, as you're looking at this function, you want to say, as I plug in bigger and bigger numbers, let x get huge, let x grow without bound. Super crazy big numbers. We want to see what's happening to the outputs as we let x get huge. And here's just a note of caution. Infinity is not a number. You can't do arithmetic or algebraic operations on infinity. Sometimes infinity divided by infinity could be 1. Sometimes infinity divided by infinity could be -7. Right? It is not a number, so be really careful about this. Now, there are certain types of limits with infinity that are simple to do, like this one in example 2.7. We have the limit as x approaches infinity of 1 plus 1 over x. Well, I'm just going to note that as x approaches infinity, as x gets super huge, the fraction 1 over x gets crazy small, and in fact it approaches 0. If I take 1 and divide it by 1/1,000,000th, if I take 1 and divide it by 1,000,000, I get 1/1,000,000th. As the denominator gets bigger, this thing gets closer and closer to 0. So when I evaluate this limit, if I see a part of an expression that's like of the form 1 over x, or in fact any constant over x to some power, some positive power, this type of fraction will approach 0. And so this limit is approaching 1 plus 0, and this limit is equal to 1. So the idea when we are doing these limits as x approaches infinity is that we want to be able to, we want to rewrite the limit. We want to use algebra to rewrite it in such a way where x only appears as the denominator of a fraction with a constant numerator. Because those fractions will then approach 0. We're going to do a couple of these examples. Our technique for making that happen is to divide the top and the bottom by the highest power of x that appears in the denominator. So here we have the limit as x approaches infinity of x squared plus 1 divided by 2x squared plus 3. We'll just note right here that if we let x approach infinity, the top goes to infinity and so does the bottom, and we can't really do that kind of arithmetic. So we're going to multiply the top and the bottom by 1 over x squared. And now what we're going to do is distribute that factor. So I've got x squared times 1 over x squared plus 1 times 1 over x squared. On the bottom, 2x squared times 1 over x squared plus 3 times 1 over x squared. You can probably see what's going to happen here. The x squareds cancel in the first term. Up top, we have the limit as x approaches infinity of 1 plus 1 over x squared. On the bottom, these x squareds in the first term cancel. On the bottom, we have 2 plus 3 over x squared. Now, look at this limit. The only places where x appears are in the denominator of a fraction with a constant numerator. I've got x to a positive power in the bottom and some constant up top. Now this approaches 0, 1 over x squared approaches 0 as x gets huge, and 3 over x squared approaches 0 as x gets huge. And so overall, the top is approaching 1, the bottom is approaching 2, and this limit is equal to a half. So in this example, infinity over infinity was approaching 1/2. Let's try another one. This is an interesting example. We want to evaluate the limit as x approaches infinity of the square root of 3x squared plus 5 divided by 2x minus 1. You know, our technique is let's divide by the highest power of x that appears in the bottom. You could alternatively just divide by the highest power of x that appears anywhere. In this case, either way you think about it, the highest power of x that appears in this limit is just x to the first. And that's because up top we have this x squared, but it's inside a square root. So in effect, it's like the highest power of x that appears is x to the first. So we're going to multiply both the top and the bottom by 1 over x. And we're going to do some algebra here. On the bottom, I'm going to distribute. And when you distribute this, I mean, we kind of probably just do the algebra as we go. 2x times 1 over x is 2 over x. And then minus 1 times 1 over x is 1 over x. So we know what the bottom looks like. I just wrote 2x times 1 over x is not 2 over x. 2x times 1 over x is 2. My apologies. So we are all set with what this expression is on the bottom. Up top, we're going to have to do some algebra. And before we can think about distributing the 1 over x, we have to bring that 1 over x inside the radical. And so I'm going to do a little side work just to kind of remind us how we can do this. We're already used to how we might simplify a radical, a square root, right? Remember that when we simplify a square root, like if I have the square root of 3x squared, I'm going to not have any addition or subtraction. I'm going to just sort of look at this product. That if I have a squared factor, right? A squared factor inside I can bring out as a single factor outside, a factor of x to the first. Now this rule about how we take out squared factors, that something squared inside is just something to the first power outside, this works in both directions. I could take this factor and put it in the radical if I square it. And so that's what we're going to do here. This factor of 1 over x, we're going to bring inside the radical. So now I've got 3x squared times, 3x squared plus 5 times 1 over x squared. This 1 over x all squared is equal to 1 over x squared. Now I can distribute that factor of 1 over x squared inside the radical. And when you distribute and simplify that, three x squared times 1 over x squared is 3. 5 times 1 over x squared is 5 over x squared. Now, the only places where x appears is as the denominator of a fraction with a constant numerator, 5 over x squared. As x grows without bound, as x approaches infinity, 5 over x squared, that approaches 0. 1 over x approaches 0 as x approaches infinity. And so the top is approaching just the square root of 3. The bottom is approaching 2. And there's our limit.